Hey everyone, welcome to Chapter 5, Introduction 5.1. We're talking about transcendentals. Okay, and you say, well, what's a transcendental? So, let's look at it. We look it up right here and we say, okay, a transcendental is either relating to a spirit or non-physical realm, or it's a number, a real number, but not a root of an algebraic equation. So guys, I'm sorry, unfortunately, it's not a medium to talk to the other world. Sorry, it's not the first one. It's the second one. It is a real number, a real equation, a real thing, but it's not just square roots or quadratics or that kind of stuff. It's got something else that goes along with it. Okay? So, let's just use this as kind of an example, as a starting point. Let's use an example of the power rule. Y equals x cubed. If we take the derivative of that, we'd say y prime equals 3x squared. Y prime for this one equals 2x, and y prime of this one equals negative 1, x to the negative second. Right? Nothing new. We've been doing that for a while. Alright, so let's take the antiderivatives of the exact same thing. So we want to say, what's the antiderivative of that? Well, we could say, like, let's just take the integral dx, and the integral dx. Okay, let's just do that. And so that would be 1/4 x to the 4th plus c. This would be 1/3 x to the 3rd plus c, and this would be 0x to the 0 plus c, and you say, wait a minute, what happens here? We kind of have a problem, and this is the only time we said, we can't do that. That does not work. X to the negative first is the only thing that does not follow that antiderivative power rule. So, what is the integral of 1 over t dt? What is it? You will ask, and I will tell you. It is the natural log of x. So we can say this. The natural log of x equals the integral from 1 to x of 1 over t dt, where x is greater than 0. And you say, what? What's a ln? Well, ln is a natural log with base e. Okay, so it could be written this way. You know, you've seen log base 2, log base 4. We've even seen log base 10, right? When we say log base 10, we really just say that's log, right? So you have log base 2, log base 4, log base 10, and log. So this is a shorthand way of writing. So if we want to rewrite log base e, that's really the same as just the natural log, ln. Okay. So now the next question you say is, so what? What is E? Great question. I'm glad you brought it up. E, there we go. E is a number. It's approximately 2.71828, and there's all sorts of other decimal numbers after that. And it is used, you didn't show up very well there, it's used in interest formula calculations if you're doing compound continuous, not just compound quarterly or monthly or yearly. It's compounded continuous. It's really helpful in that kind of thing, and it's also written as this sum. The letter E no longer stands for only letters. It is a number about 2.7, and it equals the sum as n goes from 0 to infinity of 1 over n factorial. So that's the same as saying E equals 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3 plus 1 over 1 times 2 times 3 times 4 plus, and so on until we get to 1 over 1 plus 2, or times 2 times 3 times a really big number. Okay, so as we get there, eventually this thing has become 0. So it's going to be 1 plus a half plus a 24. It gets really, really, really small, really, really fast. Okay, so it ends up being about 2.7. Okay, there we go. So why do they use the letter E? I mean, we could have used X. We could have used, there's 26 letters. We could have used Y, E. Well, it is because well, let's just look it up. Why don't I have to do that? Why don't we use the number E? The number E is for this guy, Euler, who has done all sorts of stuff for us with math. E-U-L-E-R, Euler. He is the guy who kind of came up with this number. He's actually got another number out there. It's a little bit different than E, so don't be confused with the Euler number and the Euler constant. The Euler, I don't remember the other guy's name, but Euler, there's another constant. It's the actual Euler number E. Okay, good. So we got a few more things here we're going to do. Theorem 5.1, properties of natural logs. We're going to be spending a lot of time on natural logs, not on other logs. So, don't be late to class. Okay. So 5.1, properties of natural logs. First of all, the domain is going from 0 to infinity, and the range goes from negative infinity to positive infinity. So let's look at what that graph looks like. All right, so let's look at the graph of a natural log. And this is what it looks like. So we said the domain goes from 0 to infinity, so it has nothing to do with negative numbers. So we put the natural log of a negative number, you get no answer. Nothing's going to happen. We can't do it. As long as it's positive or greater than 0, not equal to 0, but greater than 0, we're good, and it'll go on forever, all the way out to infinity. We can zoom out, and this is just what happens. So you see we're up to 100, we're up to 250, 3, 4, 5, 6, 8. So we're out. See how it just stays, it continues to go. Okay, great. So we know the range goes, or the domain goes from 0 to infinity. The range goes from 0, or negative infinity, to positive infinity. So we know that it keeps on going down forever. It goes to the right forever. It goes up forever. It just doesn't go to the left. That's the only problem. Okay, good. The function is continuous, increasing, and 1 to 1. I don't think we've ever talked about 1 to 1 before. What 1 to 1 means is that you remember the horizontal line test, where we say it passes the horizontal line test, which means it's a function. Well, if it passes the horizontal line test, great, it's a function. If it passes the vertical line test, I should have said that. If it passes the vertical line test, then it's a function. If it passes a horizontal line test, then it is a 1-to-1 function, which means each input only has one output. One input, one output, 1, 2, 1. Got it? Great. So that's what it means to be a 1-to-1 function. So an example of something that's not a 1-to-1 function, quadratic, y equals x squared. Right? Y equals x squared. Oh, I can't do that. Let's do this really quickly. Y equals x squared. If we look at this one, it's not 1-to-1 because it doesn't pass the horizontal line test. At y equals 2, there are 2 values. At y equals 4, there are 2 values. That doesn't work. That's not a 1-to-1 function. However, the natural log is. Okay, the graph is also concave downward. If you look, it opens concave down. Very good. Okay, so then, here's the last thing we should know for this video, and that is Theorem 5.4. The derivative of the natural log of the absolute value of x, or the absolute value of u, or whatever letter you want to use, equals u prime over u. Okay, that's it. I will have a video up for doing log, just review properties of logs, and then we'll also have another video on just some example problems. So there you go. Have fun.